Hi all, thank you for coming to the talk When GPUs Make Python Slower, Patterns and Pitfall. Let's give a warm welcome to our speaker, Kaashif. Kaashif, the stage is all yours. Thank you.
Hello, everyone. I'm Kaashif. I work at Bloomberg. And this talk is about when GPUs make Python slower, patterns and pitfalls. So I'm glad we had a talk just before this one about how CuPy numeric makes your code faster, because this talk is really some advice about how to avoid making your code slower, which is kind of the opposite, but should hopefully be a bit helpful. So here is the summary of the entire deck. So after you see this slide, I guess you can leave. I apologize to the experts in the audience who are interested in deep dives on how to write good CUDA kernels and that kind of thing, because that is not exactly what this talk is about. What this talk is about is how to avoid some of the fixed costs that come up when you're writing GPU code that you may not be used to if you're writing code that runs on the CPU using pandas or some other library for data analysis. So just to quickly run through what all of these things are. So minimize memory transfers. I mean, this one's pretty simple. So when you are running code on the CPU in the CPU's memory, so RAM, and you want to run that on the GPU, you have to move some bytes across the PCIe bus to the GPU. That takes some time, and you should minimize how often you're doing that. Maximize operational intensity. So I'll explain what this is with some examples, but effectively, what I mean there is that you should move a small amount of data and do lots of computation with it, rather than moving lots of data and doing a small amount of computation on it. So there are some, I think, canonical examples of problems that are a good fit for a GPU and a good fit for a CPU, and I'll go through some of those examples and some code that implement them. And the last one is a bit different, so don't launch lots of small kernels. I mean, this is a minor point. You can launch lots of kernels, you can launch small kernels, but when you launch millions of small CUDA kernels by accident, by converting some pandas code to run on the GPU, that can absolutely tank your performance, and it may not be obvious if you haven't seen some of these profiles before. So I'll go through an example where some pandas code that was really fast, really vectorized, really cache-friendly, becomes slower when you have the same code running on the GPU. So to motivate all of this, let's look at a problem. So this is a pretty simple problem. So on the left, you have some headlines. These are not real companies. And we're looking for this regex, so whether the string contains this rather simple regex. And what we might be doing here is trying to see, is this news story related to this company Acme or not? And we get some booleans out on the right. I actually didn't check if Acme is a real company. It might be. I think it's not. So what does the pandas code that implements this look like? Very simple. You get the text column, you check if the string contains this regex, and there is some very simple and rudimentary timing code there as well. So this isn't a detailed, statistically powerful benchmark. It's just something so we can get a sense of how quickly this code runs. I do want to give a disclaimer about some of these benchmarks. When I'm benchmarking some of this code, specifically the GPU code, I'm doing this in a very coarse-grained way. I'm not using the CUDA event API. I'm not running things asynchronously. So this is really for us just to get a sense of what's going on. And these graphs should be regarded mostly as pretty pictures. And the real information will come from the profiles, which we'll look at also. So how fast does this pandas code run? I ran this on several examples of data frames. On the x-axis, on this graph, we have the number of rows in millions that we executed this code on. And on the y-axis, we have the number of rows per second that we got when we ran this algorithm. So the thing that what I'm trying to demonstrate here is that the performance is pretty constant in terms of rows per second, because I made the data set large enough that there are no weird cache things going on. The data doesn't fit in L1, L2, or L3 cache, and the strings are large enough that 1,000,000 rows is enough to induce that. But also there are no weird fixed costs associated with this that amortize out as we increase the amount of data. So this is fairly constant, and maybe if I ran more iterations of this benchmark, this would even be a flat line, but I didn't. So here's a question: how do we make this faster? So I ran this on a CPU that has 16 threads, but if you run this on a GPU, you have 6,000 CUDA cores. So, and this is to scale. It might not be to scale, actually. I retract that. But we have a lot of CUDA cores, and surely we could get 100 times increase in performance. I know that's not exactly right, and I know that cores on a CPU are not analogous to CUDA cores on a GPU, but the point here is still valid. GPUs have lots of cores. That's the point. Now, luckily enough, there are these libraries out there that exist that allow us to take advantage of all of this parallelism without having to rewrite all of our code. You've already seen one example if you're in the room for the previous talk with CuPy numeric. But in this example, I'm going to use cuDF. So cuDF allows us to write this, and the business logic here, i.e. the string contains regex line, is exactly the same from the Python programmer's standpoint. The difference is in these two lines, where we move some data from RAM to VRAM, and we move some data back from VRAM to RAM in order to get that data back into the CPU where we can do something else with it. Now, I know here I'm using CUDA kind of as a black box accelerator for this one function, and if you're doing a lot of other processing, you shouldn't do this, but that is the kind of the point of this talk. As in, I will show you some things you shouldn't do, and then later on, I will show you some things that you should do. So between these two functions, the pandas regex matching and the cuDF regex matching, which one do you guys think is faster? So please raise your hand. Remember, this talk is entitled When GPUs Make Your Python Slower. Now, raise your hand if you think the GPU code is faster. I worry I biased that like way too much because no one raised their hand. Raise your hand if you think the CPU is faster. Now look, I tricked you because the GPU is way faster in like all cases. But there is this one case right at the start with a small number of rows where cuDF, as in transferring the data over to the GPU, processing it, then back, is actually slower than pandas. But in all other cases, the GPU was actually faster. There is an effect you can see here. So this, the performance graph here appears to be converging to some value. The reason that is because there is this fixed cost of doing all of this that we're amortizing out as we process more data. So if we had even larger data sets, we would see some flatter line here. The reason if you're wondering, the reason the range is so wide there, and I took the average and that's what you see, is that the performance varied a bit, as in I was measuring some noise there. So I ran, I think, 100 iterations, and that's the average to get your nice curve. Okay, so what is the business strategy of a GPU company then? It's this. It's make more cores. This is a real photo of a business strategy meeting at a GPU company. Unnamed, make more cores. Okay, so let's go back to this graph. So there are a couple of things I mentioned that I didn't really explain. So there's this part here, which is the small region of this graph where the CPU is actually faster than the GPU. What exactly is going on there? Can we profile it to prove out my as yet unproven hypothesis that this is due to bytes moving across a bus from the CPU to the GPU? And also, Didn't I say that there were like 300 times as many cores on a GPU as there are on a CPU? How come this isn't like a much larger gap here? It doesn't appear to be converging to some 300x value. This is just like 3x. So what is going on here? So one way we can tease out the differences here is by changing the problem a little bit and making the strings and the data a bit larger, but keeping the computation the same. So here is a slightly larger string, but the problem is the same. So we take this huge string, we search it for this regex, and we get a Boolean out. And we do this for lots of larger strings. So in this case, what we see is that the GPU is actually slower, and the performance here is not converging or rising to some larger value. You can see there, incidentally, that the pandas line is a bit wavy. This is why I was saying that the benchmarks are for entertainment purposes only, because I've already proven my point by having the lines above each other. I didn't need this to be a flat line. So please ignore that, but the point is that when the data is large and you are doing not very much computation, the GPU isn't a good fit for that. And why, you may ask? We can use one of these tools that NVIDIA provides. I can't say unnamed GPU company forever, right? I have to actually tell you what tools I'm using. And if we look at this tool called Nsight Systems, which provides a timeline of what is actually happening with the CUDA kernels running on our GPU, you can see that there's this huge purple bar. And that bar is the data frame .fromPandas function. And this entire thing basically represents the cost of I/O, of moving some bytes from one place to a different place across a memory bus. And that is taking up the vast majority of our time here. And only this tiny sliver right at the end is actually any compute at all. So this is where our regex matching actually happens. And that huge green bar, by the way, is just memset. I mean, we're spending multiple times longer just setting memory than we are computing anything or matching regexes. So that's not ideal. And if your problem is of this shape, probably you just shouldn't do it on a GPU. So to hammer home this point, you're copying data from RAM to VRAM, and you're copying it back. If, in your case, your data is very large and your computations are very cheap, then this is going to be a very bad fit for a GPU. So please minimize memory transfers. That would be my advice. So I know what you're thinking. For the experts in the audience, this won't be a surprise, but for anyone who isn't familiar with GPU programming, you might recall that matrix multiplications in linear algebra are supposed to be very fast on GPUs. After all, we've heard about machine learning, we've heard about AI. All that's going on in there is computation, data moving, and that kind of thing. So how come what I said be true and that also be true? And it is indeed true that if you do a matrix multiplication on a GPU, it is obviously way faster than doing it on a CPU. Now, this is just some random code I wrote with CuPy doing a matrix multiplication of various sizes of matrices. And you can see here that, again, the shape of the graph is not that important. The point is the GPU is much faster. And if I spent some time optimizing this, I'm sure it would be faster still. So what is going on here, and how can we rigorously identify when a problem is a good fit for a GPU or not? So this is how you can do it. If you're doing a regex match, you have a linear number of operations. So there L is the length of the string. So the number of operations here is linear in the length of the string. But when you're doing a matrix multiplication, you have a very differently shaped problem. If the dimension of the matrix is n, then if you want to calculate, in this case, Cij for all I and j, you have on cubed operations. Now, so the input size is on squared in this case. So there are various algorithms you can use. You can reduce the exponent a bit, but the point is that the number of operations is larger than the input size and scales differently. So to see this a bit more visually, we can refer to what's called a roofline analysis, because it kind of looks like a roof. So on the x-axis here, you see the operational intensity, so operations per byte. And on the y-axis, you see the performance of the algorithm in total, so taking into account all of the memory transfers, all of the computation. When you take the number of operations, divide by how long it took, how long did the whole thing take? So regex match occupies a space here on this graph. What that means is it has low operational intensity. So on this line here, the bound based on bandwidth line, you see that we're limited here by memory bandwidth. So we're doing a memory transfer, a huge memory transfer, basically no computation, and then we're sending the results back. So that occupies a space far on the left of this graph, whereas matrix multiplication occupies an entirely different space over here. So what we're doing there is we're moving some data, we're doing a lot of computation on it, so we're limited by the computational speed of the GPU. Here on the line labeled bound based on peak performance. So we're further to the right. So this problem is limited by the compute that you have available to you and not just the memory bandwidth. So that's a better fit for a GPU. So we can quantify, so this graph is fake, like I just put this dot on there. We can see this in reality using a tool called nSight Compute. So for the regex match, if you run that algorithm under a profiler and you look at this DRAM throughput statistic, you can see that it's, in my particular case, 92%. So we're really maxing out the memory bandwidth there. And if you look at the compute throughput, so SM meaning streaming multiprocessor, so this isn't a talk about GPU architecture really, so I won't explain blocks, grids, streaming multiprocessors, etc. But it's the compute throughput of the GPU. You can see that number is much lower at 35%. So there we're bound by the memory throughput, and we're not bound by compute throughput. So probably not a fit, probably don't do this on a GPU. For a matrix multiplication, on the other hand, so I was hoping that this number would be something close to 100%, but I didn't spend very much time optimizing my code or pipelining operations or running them asynchronously to enable latency hiding or anything like that. It's just multiplying one big matrix. So this number, 65% compute throughput, is intended to demonstrate that we're closer to utilizing the full power of the GPU. But the more notable thing here is that we're really not even slightly maxing out the memory bandwidth here. So the DRAM throughput, as in loading things from global memory, is 7%. So that's not very intense at all. So the lesson here is that you should understand the operational intensity of your code, of your algorithm, and you should maximize it. So you should know the shape of your problem and be able to tell me, is this problem a good fit for a GPU, or will it become a good fit after a certain data size? Because sometimes you get those small data, big data problems, but you've got to understand the shape of your problem. Okay, so this is the second lesson I wanted to convey. The third lesson requires us to look at a different problem. So on the left here, you can see some data. So we have an ID column, each row representing perhaps a financial security, like a stock or a bond, and each column representing some time period, in this case, a day. And the value in each cell is a price, let's say. So for example, in this case, you have security 1, the price went up a bit from day 1 to day 2, and the other security, the price went down. And what we want to do is count for how many days was each of these securities in this range of prices. So 90 to 100 not inclusive. So in this case, obviously security 2 had that be true once, and security 1 never had this true. So let's write some pandas code to compute this. So it's pretty simple, I think. So we initialize the series with zeros, one for each row, one for each security, sorry. And the point here is that what we're doing is we go through each column. We evaluate the condition for each row in the column. So was this value in the range 90 to 100, not inclusive? And then we keep track of the counts for that whole column. So in this case, that value is in the in-range counts function, in-range counts variable, and we return that, and that's the value we're looking for. So I want to refer to this as the wide format of the data, because it's wide. It has, the more days you have, the wider this data set is going to be. And that is the dimension along which this kind of data set tends to grow. We're processing it column by column. So columns are laid out contiguously in memory, so this has good data locality. You'll be using vectorized instructions when you add these columns together. So you have your columns of zeros and ones, your columns of counts. You add them together. That is going to be very efficient. And this is very cache friendly. So we're accessing data in order with good data locality, with vectorized instructions. It's going to be very fast on a CPU. But, so here's the data we had. There's another format, which is probably more common, that we get data in. And that looks kind of like this. So instead of having a column for each day, you have a row for each day for each security. So on the left, you have the ID column, same as before. But instead of having different columns, we have days 1 and 2 encoded as values in that column. So each data point has a row associated with it. But we still want to do the same computation. So count the values, the prices that were in this range for each security. So what that looks like is this. So it's conceptually the same kind of thing. So we filter down to the rows that have the price in the range that we want. We group by security ID, and then we take the size of each group. And that gives us the same value as before. The difference is how we're processing the data. So the inputs and outputs are the same, but the performance characteristics are very different. So the tool format, so each row is what we're processing. So this is processing data row by row to read out the price, the day, and the security ID. There's some duplication here. I mean, that's not a huge issue. If you have 100 of the same string and you're storing that data as maybe something arrow encoded in memory, that'll be encoded efficiently and won't actually duplicate the data. But it does, when you print that out, look kind of duplicated. But the code is simpler. I mean, it's closer to encoding our intent rather than encoding some kind of procedural algorithm that doesn't match with how we explain what we want. So there's pros and cons. But what we really care about is the performance characteristics of this. So I ran a benchmark, and indeed it turns out, because of the way I phrased this, hopefully this is expected, that the wide format, which is processed in a column-by-column, cache-friendly way, is much faster than the tool format, which is processing row-by-row in a cache-unfriendly way. And if these columns are large, these memory accesses can be very far from each other. So this can be really cache-unfriendly. So that's unsurprising. So next step, let's run this on the GPU. So this is almost exactly the same code. The only difference is that we have a cuDF series instead. So this is odd. So I didn't flip the colors there. What actually happened is that the tool format, which was supposedly cache unfriendly and terrible in performance, is now much faster. And it looks like, with the number of columns that we have there, we haven't even maxed out the performance yet. We haven't even reached the plateau in the curve. So this is like crazy, right? Like you had this naive translation or this idea that if you translated your code to cuDF, it would be much faster. I mean, in this case, the wide version of this cuDF code is so slow. It's actually slower, not just slower than the tall version of cuDF, but also slower than both pandas versions at all numbers of days that I've tested here. So that is pretty crazy. What is going on here, and how do we avoid making this kind of mistake in the future? So let's look at the timeline. What you might notice here is that the previous culprit, the purple bar where we create some kind of memory structure on the GPU, is tiny. It's off to the left. Instead, what is taking up the most time is whatever this is. And this isn't one huge bar. This is thousands and millions of smaller bars. What is that? I mean, we can open Nsight Compute and have a look to see the duration of all of these kernels and the names. That might be a bit tough to see, but these are all binary operations on cuDF series. So what is happening here? I mean, these are all taking microseconds to run, but the thing to note here is that this isn't like either the regex computation, where we were maxing out the memory throughput, but not the compute throughput, or the matrix multiplication, where we were maxing out the compute throughput, but not the memory throughput. In this case, we're getting an absolutely abysmal 1 to 3% throughput on both compute and memory. And even with the suggested optimizations from Nsight Compute, this only suggests a 50% improvement. So yeah, maybe we'll get 2% or 4% utilization of our GPU. So something is going seriously wrong here, and it is localized within these binary operations. So that's what's going wrong here. You'll notice that what's happening here is not data transfer from CPU to GPU and back, but control flow transfer from CPU to GPU and back. So what is happening here, and the anti-pattern that I want to focus on, is that we have this for loop in Python that's running on the CPU, running extremely tiny bits of work on the GPU, and thousands of tiny CUDA kernels that take mere microseconds to run. This is not how you should write these code. Please do not have this many CUDA kernels doing this tiny amount of work. Don't launch lots of small kernels. It's a waste of time. There's overhead when you launch each kernel. And yes, it is true that if you run lots of kernels asynchronously, you pipeline, maybe it would be fine. But a much better way is to just run one big kernel if you can. And even better, the cuDF code is very optimized, very performant. So there are many optimizations you can benefit from if you let them handle it. So the group by, the counts, they're doing the right thing. So don't launch lots of small kernels yourself. So just to run through this again one last time. So the basic concepts here are to minimize memory transfers, don't move data back and forth from the CPU to the GPU and back. That actually does take a lot of time. Maximize your operational intensity, so don't run problems which are kind of search-like, as in they transfer a lot of data and do little computation on a GPU. And don't launch lots of small kernels. So I see this sometimes when someone is writing CUDA code for the first time. They're naively translating their code. They run into a lot of these anti-patterns. Very easy to avoid. Hopefully doing the right thing is simple. So please follow these steps, and I will refer you to the next talk if you want to learn about how to write a good CUDA kernel, which is also in this room. But for now, hopefully you have realized that there are these things you shouldn't do, and they completely ruin the performance of your code. So here's the advice. Please follow it. And the last slide. So thank you for listening, obviously. If you want to learn more about how Bloomberg writes Python, go to tech@bloomberg.com/Python. And Bloomberg is hiring. Bloomberg is also sponsoring this conference. You heard about some of what we've done or what we do from Andy in the keynote, or before the keynote, I should say. And go to bloomberg.com/engineering if you would like to be hired by us. So that's it. Thank you.
Thank you, Kaashif, for this wonderful session. So I guess we have 1 minute for few questions. So if anyone wants to ask questions, they could use the mic at the end.
Hey, thanks for the talk. I wanted to ask, how difficult was it for you to use Insight Compute, Insight Systems, if you could talk a little bit more about that, and any other tools you find useful when you're debugging performance with GPUs?
So Insight Systems and Insight Compute are super easy. I mean, you can run your Python code basically as is, just under Insight Compute and Insight Systems. The magic is that if you only care really about the CUDA kernels, the CUDA kernels running here are like the same as what's running if you wrote a CUDA kernel in C++. They're just, I guess, written by someone else and under the hood in cuDF. So super easy. And I advise you, for other tools that are helpful, I advise you to look at that website. Insight has a whole suite of tools that are super, super helpful and easy to use. So that would be my advice.
Thank you.
Hey, great talk. I really like your point about minimizing memory transfers. I was curious, did you run any benchmarks where you did the I/O with cuDF as well?
So I could do that. That would be the other way to do this talk. So when you say do the I/O with cuDF, you mean, what do you mean exactly?
Like calling, if you have data at rest instead of data at memory, for example, you could call read CSV or read Parquet from cuDF.
Right. So the point of this, what you want to do, I think the data has to get from disk to the GPU somehow, and if you do that in one go, however you do it, it's going to be better than doing that many times. So I don't have a benchmark where we did that. Usually how it works is we get data from some other system and it's already in memory, in the CPU's main memory. So that's the standpoint from where we're processing this data. But you could do that. I'm sure it would work great. The point is, don't do lots of I/O all the time, constantly. That's terrible. Don't do that.
Awesome. Thank you. I would add GPU I/O is one of the things that you can do that makes the biggest impact for this. Even if you do your entire workflow on CPU,
yes,
just doing the data read on GPU will give you good performance.
Yes, I agree, but that's not in this talk, unfortunately. You should give a talk.
Check out my talk from last year. It talks about cuDF pandas
nice,
and many of these same topics. It was
I
in
may
this
have
room.
watched your talk, actually.
This room 1 year ago. So yeah, happy
nice,
to talk more about cuDF.
Okay, great. I think we ran out of time for questions, but thank you, everyone.